Number 2, you might remember it from 9th grade. So this is exponential growth and decay. So following what we just went over in the Able with a Table page, we're just going to build our function and plug it in our calculator, fill in a table. So right now the population of our town is around 25,000 people. However, the number of citizens is projected to increase about 8% every year. What will the population be in 4 years? What is my initial value, my A? 25,000. So I know my first thing right here is going to be 25,000. And right here, my A value is 25,000. Now, my increasing rate is 8%. Okay, so be careful though, because it says it's increasing. And if I change 8% to a decimal, that would be 0.08. And if I put that here as a base, what's that going to cause my table to do?
1.0.
Decline, right? It's exactly. So what is it going to be?
1.08.
We're going to have to put in 1.08. We have to account for the fact that 100% of the initial population is still there. And then we add 8% to that. So that's why we put 1.08. Alright, on number 2, Old MacDonald bought a farm tractor for $60,000. For tax purposes, its value is expected to depreciate at a rate of 18%. What will the tractor's value be in 4 years? What's your initial value?
60,000.
60,000.
Yeah, that's a lot for a
And my base, so this time I'm depreciating by 18%. Now, I don't have 18% remaining. It depreciates by 18%. So what's going in here is going to be 0.82 because it starts with 100% and it depreciates by 18%. Okay. Now we have a manufacturing plant sending 50,000 cubic feet of CO2 into the atmosphere annually, but they've signed an environmental agreement to cut the emissions by 12% each year. To what level will the carbon emissions drop in 4 years? What's your initial value? If I'm agreeing to cut my emissions by 12%, that means you would have 0.88 remaining. On number 4, they gave us the table first. What's your initial value going to be, or your A value?
5,000.
All right, so 5,000. And now I'm going to divide. It doesn't matter which 2 values you choose in your Y table. Just remember you divide going up the table. So I get 1.06, which means what is your actual rate of increase? Yeah, 0.06 or 6%. All right, is everybody okay?
Yeah, we're good.
Yeah, this is pretty easy. All right.
This one's
growth function. We'll do decay in just a minute. It's growth because it has addition. So it has that 1 in it that we talked about, representing the original 100%. The A naught, or the A, so A with a little 0 at the bottom, that's what we call A naught. That's your initial value. So these particular problems on this page are all interest, financial interest. If we were using this top one, that would be when we're using just an annual interest rate and they're paying us interest one time a year. But financial institutions often will pay us interest more than once a year. It's called compounding. They choose how many times they're going to give you a little bit of interest, and it's to your benefit because then the next time they calculate interest, you have a little bit more money in the bank. So in that case, we use this formula where N represents the number of times compounded. R is still your rate, T is time. So we're looking at number 5. We have a $6,000 investment at a 4% annual interest rate for 5 years. How will the investment change if the interest is given ahead of time? So on the first one, they did it annually. On the one that they've left for us to do first, they want us to calculate this compounded quarterly, or 4 times a year. So our end value is going to be 4. Our initial value is going to be 6,000. Our rate is 4%, so we're going to write that as 0.04. In the formula, you can see the formula right here. It's rate over times compounded, so quarterly is 4, raised to the NT, or 4 times T. Now I'm going to go put that in my calculator. Your calculator does not understand anything but x's and y's, so we're going to put it to the 4x power. It would benefit you to use your fraction bar because this gets all crazy with closing parentheses and stuff if you don't. Alright, so I plug it in. Looks like that. 6,000 times 1 plus 0.04 over 4 raised to the 4x power. And then I can just go to my table. Alright, so I don't know if you know this about your table, but on a TI-84, the column width is set. It can't be made wider. So it cuts off decimals, but if you highlight it, you can see down in the bottom what the actual value is. And in this case, it's important to us because it's money. So we need to go to 2 decimal places. So it would be 6243.62. Anybody have any questions on those so far? Everybody okay? Everybody get it in your calculator okay and get the same answers I got? No. No. Okay, so the divide by 4 is by itself. So does that make sense? Anybody else have questions? All right, so on the next one, we're compounding monthly, which means they're going to give me my interest at the end of every month. So that means they're going to give me interest 12 times a year. All of my other values stay the same. My initial value is $6,000. My rate is still 4, so 0.04. But my end value has changed to 12.
Can you just go in and change that?
Yeah, I'm just going to go in and type over instead of 4, I'm just going to change that to 12.
So easy. I think like 12. Around that range. Yeah. Is it? Oh, sorry. So what one did I send you? That looks like the last one.
Oh, I know what's wrong. It should be 0.04.
Oh, yeah.
Give it as 0.4, so it's like 40%.
So,
All right. The next two. So look, you can see already that the more often they pay us interest, the more money we make. Now it's not a lot, but it's a little bit for doing nothing. I mean, so if they were asking, if they were going to pay you interest every week, what would your end value be?
52.
52. Everything else would stay the same. Still 4%. We just changed our end to 52. Now on this one they did 52 times 5 because they're just going to calculate it on the main screen because they didn't want to get all the years in between, fill in a table. So they're just putting it on the main page.
Plug it all in how it is.
That's basically the same.
And what if they are going to pay you interest every day? 365. And in case you didn't know, financial institutions always calculate with 365, even in a leap year.
That's crazy.
That's just the way they are. Anything to save themselves $1.
Yes, it does.
All right, is everybody good? Not hard, right? Pretty simple. Next page is decay problems. So this first example is radioactive material. It loses mass over time because some of its nuclear mass is released as radiation. The mass of certain sample changes according to the equation at the left. After approximately how many years will the sample have only half of its original mass? We call that a half-life. So we're going to plug this into y equals.
I thought this was retail and science.
They are very, very closely related. Just wait.
I'd rather know.
You have to do it right now.
All right, so my initial value was 500. So what would half of that be? 250. So in this case, we get to 250.12 after 4 years. So our half-life is essentially 4 years. Now, the next bullet asks the question, is all of the substance gone after 2 half-lives? So 2 half-lives would be 8 years. So if I go down to 8 years, is it all gone? So let me ask you a question. When will it be all gone? Never, right? Because you can half things over and over and over, and they will never go to 0. Because if you're halving something, there's still half of it left, right?
Yeah.
Mathematically, what is this mathematically reaching?
Asymptote.
Yeah, it's reaching an asymptote. It can't ever get below that value. So
Go down to 40. It's like, oh, wait.
To go down to 80, you started saying E's, and I love that.
1200.
Well, I don't like it.
I'm going to divide up my table to get my base. .891. We're going to stop right there. We'll start there tomorrow.